Welcome to Mathematics, Paper 4, Mechanics 1 of the year 2012, the May use session, the first variant. And let's go to the first question. Now in this question we are told a car of mass 800 kg, so we need to keep that one in mind, travels on a straight horizontal road. We are going to see why we've been given that, with its engine working at a constant rate of P watts. This is the symbol for power, and these are the units of power, watts. The resistance to the motion is 700 newtons. At an instant when the car's speed is 1600 meters per second, its acceleration is 0.625 meters per second squared. Find the value of P, that is the power of that engine. I usually like to approach this kind of question by first of all drawing some diagram or a sketch. So I'm just going to draw this sketch that enables me to indicate the forces which are acting. For example, there will be the force due to the engine, which we are going to regard to as the driving force, Fd. There is the resistance to the motion, 700 newtons. So this is resistance to the motion is 700 newtons. There is the mass of the car. It is 880 kilograms. And we are given that at a certain instant of time, the car's speed is 1600 meters per second. So we're just going to indicate this one with this. V is 16 meters per second. Its speed is that much when its acceleration is this much. So down here, or even up here, I can even put that arrow, double arrow. We usually use double arrows to represent acceleration. So the acceleration is 0.625 meters per second squared. Now we've got all the information on this diagram. When we look at the question, we are asked to calculate the power. You see that in this equation, there is no power. When we look at the equation for power, which is usually work done divided by time, work done is a force times distance divided by time. Now, since this one is an engine, this one will now be the driving force, Fd. This is the driving force. When we break down this equation, we can see that we can separate the d and the time, so that when you divide the distance by time, you're going to get speed. This equation finds application when the speed of the vehicle is uniform throughout, or at an instant of time. So this equation will be appropriate to use. So you can see now, instead of Fd here, we could simply say it's power divided by that speed. Or we could work out that driving force and then later on use this equation that power is equals to driving force times the speed. Here I've just made Fd to be the subject by dividing both sides by V. This equation, where we say that power is equal to driving force times speed, finds application in two situations, and you will always be looking for those two situations. It finds application at a given instant of time when either the acceleration or the speed is given, an instant of time, or the other case whereby this equation finds application, power is equals to force times speed, is where the speed is constant throughout. And you can see that one of those situations is here at a certain instant of time. Now I also want to explain these two words here, where you've been told that the road is straight and it is horizontal. We know that there are two things which describes the velocity of an object: the magnitude, which is a number and the unit, and the direction. The magnitude and direction. Over here, if the velocity were to change, then because it's moving in a straight line in the same direction, then we regard the direction to be uniform. So the only way in which the velocity can change is through its magnitude. And we've been given the magnitude here. The other reason why we are told that it is horizontal road is so that its weight, which is a type of force, will not constitute to the forces which are acting on the car here. Because this friction, it may be due to air resistance or even the actual friction between the tires and the road. They have not specified that, and we don't need to know it. So that's the main reason why you've been given this, so that if there is any change in the velocity of the object, then you will know that it comes in as a result of change in the magnitude. And then since the road is horizontal, you ignore the weight. Let's go back to the situation. We've been asked to calculate the power. So when we are told that an object is accelerating, then we should know that there is a resultant force acting on it according to Newton's second law of motion. F is equals to ma. This is the resultant force which is acting on that object. Number two, we go back here and try to find out, is the acceleration of the object given? If the acceleration is given and the direction is given, then we know that since the acceleration is to the right, the resultant force which causes it must also be to the right. So we know that the resultant force is acting to the right. So we go back and look at the forces which are acting on the object, and we can see there are two of them. There is a driving force and there is the resistance. Because the object is accelerating to the right, you conclude that the driving force must be larger than the resistance. So when it comes to arranging those two forces here so that you can get the expression which represents the resultant force, you obviously know that you'll get it by doing Fd minus Fr is equals to ma. So it's very important to realize that if you know the direction of the acceleration, then the resultant force must be in that direction too. If you know the direction of the acceleration, then the resultant force must be in that same direction. Next, if you're given the two forces which are acting on the object are acting in opposite directions, then you should know that the force which acts in the direction of the acceleration must be larger than the force which is opposing that. So if you've got to get the resultant force, then you should do the force which is acting in the direction of the acceleration minus the force which is opposing that. And that is why I wrote it like this. Of course, we know that this one is power divided by the speed as given in this equation here. The speed is 16. The resistance is 700. The mass is 880 times 0.625. And this gives me 550. 550. So the power is going to be equal to 550. I add 700. All that, because this one is power divided by 16, I can multiply both sides by 16, and that is what gives me 20,000 watts. And that is how we would get the answer to question 1. Let's go to question 2. In question 2, it reads like this. Forces of magnitude 13 newtons and 14 newtons act at a point O in the directions shown in the diagram. The resultant of these forces has magnitude 15 newtons. Find the value of theta. That is the first part. So let's work out the first part before we go to the second part. You know very well that when you're given two forces acting on an object and you're asked to find the resultant force of the two, that is the sum of the two, or the one force which represents the two of them combined, what you need to do is to connect the two forces in such a way that the head of one of them is connected to the tail of the other. As it is right now, the two forces are connected tail to tail. We cannot be able to find the resultant force from here. So the first thing is to connect the two forces head to tail. Now, how do we do that? We can do it this way. I can get this force and then I slide it to the right all the way until its tail makes contact with the head of the 14 Newton force at this point. Or I can get the 14 Newton force, slide it upwards like this until its tail makes contact with the head of the 13 Newton force. So either way, you'll find that the resultant will be from the first tail to the last head, which will be somewhere around here. So let me do exactly that so that you can be able to see how it is done. And remember, when you are doing this in the exam, you don't need to be this accurate. I'm just doing this because I want to illustrate the point so that they're very, very clear to you, so that you don't have a problem in understanding what I'm talking about. So you can see that I've drawn a line which is parallel to the 13 Newton force, and then I slide that. So forget about the 13 Newton force for the moment, because the force that we now have is the 13 Newton force, and it is exactly at this point. So this is 13. This angle theta has come here. So this is where theta now is. So I have successfully connected the two forces head to tail at this point. To get the resultant, I just need to draw a line from the first tail all the way to the last head there. And this force will represent the resultant force in direction as well as magnitude. We know that its magnitude is 15 newtons. So it is this force that we have here as the resultant force. So in this triangle, we have a triangle with the three sides which are given, and we are required to find this angle here. So the rule that we are going to use here, the most appropriate rule, because we don't know any of the angles inside here, is the cosine rule. And the cosine rule states that 15 squared, that is its application in this particular problem, 15 squared is equal to 13 squared plus 14 squared minus 2 times 13 times 14, then multiplied by the cos of the angle which is opposite the 15 Newton force, which is cos theta. Of course, this one now gives me 225. This gives me 169. This is 196. You can confirm these values using the calculator. You've got 364 cos theta. So let me quickly now work this one out, because now it's just mathematical manipulations. This will give me 365 minus 364 cos theta. And I find it appropriate to move 364 to the left or across the equal sign, so that that minus sign can disappear, and so that when I do the subtraction, 365 minus 225, I get a positive number, which is 140. This implies that theta is going to be equal to the cos inverse of 140 divided by 364. And let me see what that gives me. So I get 140. I divide by 364. I get 0.3846, and that number is recurring. Then I can go right ahead. While the number is still on my calculator, I can just get the answer, or the theta. Or let me just write this one for the sake of you being able to confirm the numbers that I'm writing here. 3846. That number is recurring, and that means that the angle theta, I'll do shift cos of that answer, and it gives me 67.38 recurring. I can just call it 67.4 degrees. 67.4 degrees. And that is how you will get the angle theta. Let's look at part 2. In part 2, we are asked to find the component of the resultant in the direction of the force of magnitude 14 newtons. In other words, what they are asking us to do here is to find this component here, this one here. The 15 Newton force has got two components. It's got a component which is horizontally to the right. It's got another component which is vertically upwards. So, in order to get this component which is horizontally to the right, this one here, which we can call the component in the x direction, fx. All we need to do is find this angle. Let's call it alpha. And then we are going to do 15 cos of alpha. I hope you can remember that when you are asked to find the component of a vector in a given direction, and that direction makes an angle, say alpha, with the given vector, then all you need to do is use cosine. You get that vector, then you multiply it by the cos of that angle. So here we've got a triangle with the three sides which are known, with one angle which is known. We need to get this angle here. At this point, we can use the sine rule. What does the sine rule state? Since it is this angle that I want, I can say 13 over sine alpha will be equal to 15 over sine theta, which is 67.4. So to get sine theta, already here I'm working part 2. So this working is meant to be for part 2. So I just note that one down because I won't repeat it. So we can get the sine alpha, which is, if I cross multiply here, I'm going to get 13 sine of 67.4. I divide by 15. Let's see what that gives us. So this sine alpha gives me 0.8000115, and that number is recurring like that. I can go right ahead and get the alpha by doing the sine inverse of this number here. Since it is on my calculator, I'll just do shift sine of the answer, and I get 53.14 degrees. We can say it is 53.1, just one decimal place, degrees, like that. That will be the alpha. Now the component of the resultant in the direction of the 14 Newton force will be 15 cos of 53.1. So we are going to say F in the positive x direction is going to be equal to 15 cos 53.1 degrees. And that will give us, it will give us 9.0 newtons. I can keep my answer to one decimal place, and it will be 9.0 newtons. And we can say, or we can just say, it is 9 newtons. So go through the working and see whether my calculations are correct. And what is most important is the method that I'm using to work out these questions. That is what I want you to pay attention to. And that is how question 2 is worked out. Let's go to question 3. Now in question 3, we are told that a load of mass 160 kg is pulled vertically upwards from rest. That is, U is 0 at a fixed point O on the ground using a winding drum. The load passes through a point A 20 meters above O with a speed of 1.25 meters per second. Find, for the motion from O to A, the gain in potential energy of the load. So let's first of all work out part 1. The gain in gravitational potential energy, we are going to call it a delta EP. Remember, it represents gain. Is going to be equal to the mass times G times the increase in height, the increase in the vertical height. The mass is 160. G is taken to be 10, and height is 20 meters. This is what gives us 32,000 joules. That is a gain in gravitational potential energy. The second part is the gain in kinetic energy. Let me create some space there. So we want to work out the gain in kinetic energy. This is represented by delta EK. Again, this is a gain in kinetic energy. It's going to be equal to half mass times the final velocity minus the initial velocity or initial speed. It's going to be equal to half times 160 times the V at point A is 1.25 squared, of course minus 0 squared. Everything is enclosed in the brackets, and if you work out that one, you're going to get 125 joules. Quite a small amount of gain in energy. And then in part 3, we are told that the power output of the winding drum is constant while the load is in motion. Given that the work done against the resistance, look at this, work done, the word is against. Resistance to the motion from O to A is 20 kilojoules. So this information pertains to part 3. So we are going to say that the work done against resistance is 20 kilojoules. But I want to change that and talk about work done by resistance. Work done by resistance. The use of this word against means there is a negative sign that has been omitted, and that is why the word against has been used. But when I talk about work done by resistance force, I put back that negative sign and we get it to be 20,000 joules. Remember, this is work done by resistance. We need to determine the work done by the driving force, so that from the work done by the driving force we can get the power, which is work done by the driving force, everything divided by time. So you can see, for us to be able to get power, what we need is work done by the driving force, because time is given. It is 41.7 seconds. So let's see how that is done. Let me create some more space down here. So we are going to use this equation, which works all the time. Work done by external forces, which is work done by driving force, plus the work done by friction force or by resistance force. Notice that I'm talking about work done by resistance force, not work done against. Work done by resistance force, because I want on the right hand side to be work done by external forces. These are external forces that are acting on the system. This principle tells us that when work is done on an object by external forces, that object is going to gain energy. The two types of energies it gains is potential energy. So this gain in potential energy, and this is gain in kinetic energy. Now this equation is so important because in all the mechanics questions that I've encountered, the examiner usually wants you to use this equation exactly the way it is, and we'll see how simple it is so long as you understand that this is gain in energy. That is why I underlined the word gain in potential energy. Delta EP is gain in, this one should be kinetic energy. I had made a mistake there. This is kinetic energy. This is gain in kinetic energy. This is gain in potential energy of the system. The system gains energy after external forces do work on the system. In fact, this expression sometimes it's written like this: work done by external forces is equal to gain in energy of the system. Just like that. But we want to break down the two very important forces that we use in mechanics 1, driving force and resistance. The two energies that we use again in mechanics 1, potential energy and kinetic energy. So let's substitute in these values and see what we get. I mean, work done by driving force plus, this one will be negative 20,000. I have already explained why the negative sign is used here. This will be 32,000. This is a very small amount, 125. And the work done by the driving force will be 52,125. So that now I can work out the power, which is given by work done by driving force divided by time. And this one will be 52,125 divided by 41.7, and you get 1,250 watts. That will be the output power of the winding drum. And that is how question 3 is worked out. Let's go to question 4. So here we are at question 4, where we are told that a particle P starts at the point O and travels in a straight line. So if we can show this kind of motion, so it starts from point O, and we can say that it travels in this straight line like this. That is the direction in which it is traveling. At time t, seconds after leaving O, the velocity p is v meters per second, where v is a function of time. This is the expression that we've been given. Find the positive value of t for which the acceleration is 0. In other words, what is the value of t when a is 0? When we are given velocity as a function of time expression, all we need to do to get acceleration is to differentiate that expression, that is get dv dt, and then we equate it to 0. So our dv dt will be like this: 0.75 times 2 t minus, we multiply this one times 3, and this one will give us 0.1875 when we multiply 0.0625 times 3, t raised to power 2. I hope you're familiar with this simple differentiation. And then once we get this, because this one is going to give us the acceleration, we equate that to 0. Equate that one to 0. So this expression, which is 1.5 t minus 0.1875 t squared is equals to 0. We can factor out t, want to remain with 1.5 minus 0.1875 t is equals to 0. So this one means either t is equals to 0. It is one of the results, or when we have 1.5 minus 0.1875 t being equal to 0 and we make t to be the subject, t is going to be, because this expression will move across the equal sign, we're going to divide 1.5 by 0.1875, and that is what will give us 8 seconds. 8 seconds. This is how we'll work out the first part of the question. So the positive value of t for which the acceleration is 0 is this much. So what does that mean when the acceleration is 0? At this point, the acceleration is 0, and there is some other point somewhere here where the acceleration is 0. Supposing we were to draw a velocity time graph for that motion. This one is not required, but it helps us to understand this situation. Now, when we look at the question, we are told that a particle P starts. Since it starts, then it means its initial velocity is 0 at some point or and travels in a straight line. So of course here, since it is at rest, the acceleration is 0, velocity is 0. There is no problem with that. But at some point, the acceleration also becomes 0. So it appears as if we do dv dt, so you can have a graph of velocity there versus time. So here the velocity is going to be 0, so it's starting from rest. If we do dv dt, we're going to get 0. That means that it must be a turning point. This must be a turning point like that, so that when we do dv dt here, we get 0. There is also another turning point here at this point where we are going to find that the acceleration is going to be 0. This is after 8 seconds. After 8 seconds. So that is, in my view, is how that situation will look like. So let's get rid of that because it has not been asked for. But like I said, it helps us to view this situation properly. So let's go on to part 2. In part 2, we are asked to calculate the distance traveled by P before it changes its direction of motion. So it appears as if this object starts from rest, it accelerates, and then reaches somewhere where the acceleration is 0. And then after that, the acceleration again, maybe it slows down. At some point, the object is going to change direction of travel, changes its direction of motion. So it will reach some point here. It must come to rest. It must come to rest. And then after that, now it changes direction of travel. That is what this question is all about. So we have to calculate the distance traveled by P, all this distance from this point to this point, because it is at this point that it changes direction of travel. And we know that when it changes direction of travel, the velocity must be 0. So what is the time taken for the velocity to become 0? We're going to get this expression and then equate it to 0. So in part 2, we get that expression, which is 0.7 t squared minus 0.0625 t cubed. We equate that to 0 because we want to get the time when the velocity is 0. And here I can see that I can be able to factor out t squared so that I can get 0.75 minus 0.0625 t is going to be equal to 0. So one of the values when the velocity is 0, and of course this is true, is t squared is equals to 0, in which case we're going to get t being equal to 0. So at the start of it, a particle p starts. This is when t is 0. And indeed, we are able now to prove that when it actually starts from rest. So let's get the other value of t. We are going to have 0.75 minus 0.0625. There's another 0 there, is equals to 0. When we arrange, we take this one to the other side of the equal sign. We are going to make t to be the subject, and we're going to get 0.75. Of course, divide by 0.0625, and this one will give us 12 seconds. 12 seconds. So the graph that I had drawn there of velocity versus time, where we saw that at this point starts like that and then moves like that. I don't know what happens at this particular point, but the velocity becomes 0. The acceleration also becomes 0. That means it is another turning point, but from here all the way to this point we are able to see that it's 8 seconds, and then now this is 12 seconds. So the distance traveled by p before it changes its direction. This is the point where it changes direction because it must slow down to 0 and then starts moving in the opposite direction. This is v, don't forget. And this is t. So to get the distance traveled, we need to calculate this area, the whole of this area. And that means we need to integrate this expression, because the area under a velocity time graph gives us displacement. So we need to integrate this expression and then use the limits from 0 to 12 in order to get that area. So in order to get that, which is s, we are going to integrate that expression, which is a 0.75 t squared minus 0.0625 t cubed dt, and the limits of integration will be from 0 to 12. So what do we have here? We have 0.75 times 2. That one will give us, so here we have 0.75 t. We increase this power by 1, get 3, and then we divide by the same 3 over here. We do the same to this other point, 0.60625. We increase the power by 1, it becomes 4, and then we've got to divide by 4, and then of course the limits of integration are from 0 to 12. This one will actually give us 0.25 t cubed minus, when I've divided 0.0625 by 4, I get 0.15625, 0.01565. You can confirm that value using the calculator. T raised to power 4, and then again the limits of integration are the same, 0 to 12. So this means 0.25, the upper limit is 12 cubed, minus 0.01565. Again, the upper limit is 12 raised to power 4, and because the lower limit is 0 and there is no constant, there is no need for writing that. We can just say minus, after we have worked out the whole of these, when we substitute 0 into this expression, we are simply going to get 0. So subtracting 0 is the same as not substituting 0 at all in that expression. So this one is going to give us 432. This expression here give us 432. You can use the calculator to confirm these values. The second will be 324. And when I subtract 324 from this value, we are going to get 108. So this is the distance that the object travels before it starts changing direction, and it is the area under the velocity time graph with the limits from 0 to 12 seconds. And that is how question 4 is worked out. Let's go to question 5. So this is question 5. As usual, we start by reading the question. The diagram shows the vertical cross-section OAB of a slide. The straight line AB is tangential to the curve OA at point A. The line AB is inclined at alpha to the horizontal, where sine alpha is 0.28. The point O is 10 meters higher than B, and AB has a length of 10 meters. The part of the slide containing the curve is smooth, and the part containing AB is rough. A particle P of mass 2 kg is released from rest at O and moves down the slide. Part 1. Find the speed of P when it passes through A. Find the speed of P when it passes through A. Now, how can we be able to do that, and yet this particle was not moving in a straight line? We can be able to use energy considerations, because we are going to look at the gravitational potential energy that the particle has here. Part of that gravitational potential energy will be changed to kinetic energy at this point, because there will still be some potential energy remaining. So what we need to do is we look at the loss in gravitational potential energy, where we actually need this height here from this point to this point in order to calculate that loss in gravitational potential energy. It will be equal to gain in kinetic energy at that point. So we need to get this height. This point, we need to get this height from here all the way to here. We need to get that and call it h. In order to do that, we can use trigonometry to calculate this height here, because we've been told that sine of alpha, which is actually equal to the opposite, we can get this one to be y. It's going to be equal to the opposite over the hypotenuse 10 is equals to 2.8. Of course, this tells us that y is 2.8 meters. So we can be able to get h. H is going to be equal to 10 meters. This 10 meters minus 2.8. And that will give us 7.2. So the loss in potential energy is equals to the gain in kinetic energy. That is the most appropriate expression to use or concept to use, because we said since it's a curve, we cannot not use equations of uniformly accelerated motion, because for those equations to work, the object must be moving in a straight line. So here we are going to get the m, g, the loss in height is going to be equal to a half m v squared minus u squared. Of course, we know it starts from rest at this point. I think we've been told that a particle p of mass that is released from rest. So there's that information confirming that u is 0. So here we have 2 kilograms times 10 times 7.2, because that is the decrease in height, going to be equal to a half times 2. Of course, even we would even have gotten this value by, if the masses were not given, they would be able to cancel out comfortably. So here we're going to get v squared minus 0 squared. So over here, I'm going to get 144 is going to be equal to v squared. And we can be able to see that v will be the square root of 144, which gives us 12 meters per second. And that is how we would work out part 1. Let's look at part 2. In part 2, we are told that the coefficient of friction between P and the part of the slide containing AB is 1/12. So from this point all the way to this point, there is resistance to motion. So let's see how part 2 of question 5 is worked out. So here we've got that object. What are the forces acting on it? There will be its own weight, mg. There will be a component of that weight acting down the incline, which is mg sine alpha. There will be a component of that weight in this direction. There's 90 degrees here, and it will be mg cos alpha, and there will be the normal reaction R, which of course is equals to mg cos alpha. And the other force acting on the particle is a frictional force acting in this direction, which actually is equals to mu r. So the first expression we realize is that R, the normal reaction, is equals to mg cos alpha. Now, since we know that sine alpha, if we look at a triangle such as, let me just draw a triangle here in order to get the expression for cos alpha. We know that this is 2.8. This is 10. We need this side, x, so as to get the cosine of alpha. Let's see whether we can be able to get x by using Pythagoras theorem. So it will be equal to, x is equals to the square root of 10 squared minus 2.8 squared. Let's see what that one gives us. Now, if you use the calculator, you're going to get the value of x to be 9.6. You can confirm that using the calculator. That means that if I want the cos of alpha, I'm going to get the adjacent, which is 9.6 divided by the hypotenuse, which is 10. So wherever I want cos alpha, I know it will be given. Now let's see the speed that it has at this point. We have just worked out and seen that it's going to be 12 meters per second. We want to find the acceleration of p when it is moving from A to B, the acceleration. So we are going to say that it's accelerating this way. Again, double arrow A. So we're going to say that the resultant force on P is equal to ma. The resultant force this way is going to be equal to mg sine alpha minus mu r, which is frictional force, is going to be equal to ma. Let's see. This one will be m, which is 2. Actually, m appears throughout this equation because here we have mg sine alpha minus mu, but r is mg cos alpha. Mg cos alpha is equals to ma. And you can see that the mass cancels out throughout, so that one is not a big problem. So I'm not going to substitute the mass because it cancels out comfortably. The value of g is 10. Sine alpha is 0.28. Let me just confirm that. Yeah, 0.28. Minus mu is 1/12. Again, g is 10. Cos alpha is 9.6 divided by 10, and that is going to give us a. So this one is going to be 2.8 minus this 10 here cancels out with this, so we get 9.6 divided by 12. That gives us 0.8. And we can see that our A is 2.0 meters per second squared. And that is how you would work out part B. Let's look at part C. In part C, we are required to work out the speed of P when it reaches B. So, first of all, we observe that the speed it had at this point is 12 meters per second. The acceleration it has down the incline is 2 meters per second squared. It is the v that we want at this point, and the s is this. And you can see that the details which are given here, they suggest we can use the third equation of uniformly accelerated motion. And let's do exactly that. So in question 5, part 3, in fact, I would have written all those details here. Let me just repeat them. The speed we want is the speed at b, which we are going to call v. The initial speed was 12 meters per second. The s is 10 meters. The acceleration it has in this direction is 2 meters per second squared. So we use the third equation of uniformly accelerated motion to help us work out the speed at b, 2as. So 12 squared is 2 times 2 times 10. So it will be 144 plus 40. And this will give us 184. And the v will be the square root of that value. Square root of 184. And that gives us 13.56, which we can say it is 13.6. So that is the speed that the particle P has at point B. And that is how question 5 is worked out. Let's go to question 6. And here we have question 6. Let's read it together. Particles P and Q of masses 0.6 kg and 0.4 kg respectively are attached to the ends of a light inextensible string. The string passes over a small smooth pulley which is fixed at the top of a vertical cross-section of a triangular prism. The base of the prism is fixed on horizontal ground and each of the sloping sides is smooth. So that tells us that there is no resistance, there is no frictional force. Each sloping side makes an angle theta with the ground where sine theta is 0.8. Initially, the particles are held at rest on the sloping sides with the strings taut. The particles are released and move along the lines of greatest slope. Part 1. Find the tension in the string and the acceleration of the particles while both are moving. So the mass of P is 0.6 while the mass of Q is 0.4. So let's see how we get the tensions in the strings. So we are going to start by indicating the weights of the both particles, this one vertically downwards. Since its mass is 0.6, we multiply that one by G, which is 10, we get 6 newtons. And this one will be 0.4 times 10, where we get 4 newtons. The component of the weight of P down the slope is like this, and it will be 6 sine theta, which is actually 6 times 0.8, and this will give us 4.8 newtons. the component of Q, while I'm still at it, the string is pulling P upwards, and that will be the tension T, and the same tension is indicated here. That tension is like that, and we indicate it like that. Notice that the two T's are facing each other. The tension in the string is always drawn in such a way that it points away from the object. The weight of the component of the weight of Q down the incline will be 4 times sine of theta, which will be 0.8, and this one will be equal to 3.2 newtons. And since this component of 4.8 is greater than this component, the acceleration is definitely going to be in this direction, this way. This will be the acceleration, and for Q, it will be up the incline. So the acceleration will have the same magnitude, but here it will be down the incline, here it will be up the incline. Because P is accelerating, first of all, I forgot to write this. This is question 5, question 6 rather, part 1. Now for particle P, because it's accelerating this way, then 4.8 is greater than T. And when we resolve down the incline, we find that when we use the equation F is equals to ma, we are going to get 4.8 minus T is equals to ma, 0.6 a. How about for particle Q? Since particle Q is accelerating this way, then T is greater than 3.2, and the resultant force will be T minus 3.2, which will be equal to 0.4 a. Again, I'm using F is equal to ma. So I've got equation 1, and here I've got equation 2. And the best way to solve them is to do that simultaneously. For example, I'll get this 4.8 minus T is equals to 0.6a, and then I write the second equation here, T minus 3.2 is equals to 0.4a. Now, since I wanted the T's to cancel out, the best way to do this is to add these two equations like that. 0.4a plus 0.6a gives me 1a, which is just a. When I add minus T plus T, they cancel out. When I add 4.8 to minus 3.2, I get 1.6. And this is how I get the acceleration to be 1.6 meters per second squared. Now, how do I get T? I will get this acceleration and substitute it into either equation 1 or equation 2. Let me substitute it in equation 2. So I'm going to get T minus 3.2. I'm going to get 0.4 times 1.6. So T minus 3.2 is equal to 0.64. So T will be equal to 0.64 plus 3.20, and I'm going to get 3.84 newtons. So the value of the tension in the string will be 3.84 newtons. And that is how part 1 of that question is solved. Let's go to part 2. In part 2, we are told that the speed of P when it reaches the ground is 2 meters per second. So already here they are confirming that P is the one which hits the ground first. On reaching the ground, P comes to rest and remains at rest. Q continues to move up the slope but does not reach the pulley. Find the time taken from the instant that the particles are released until Q reaches its greatest height above the ground. So let's use this slide here. When P eventually strikes the ground, it covers this much distance, and because the string is taut, Q will cover the same amount of distance here. So we can call that distance x. So this one also travels through a distance x. When it strikes the ground, it has a speed of, we've been told it has a speed of 2 meters per second. That means Q has the same amount of speed, 2 meters per second. Again, this is on account of the fact that the string is taut. It does not stretch. Now, as soon as P hits the ground, the string becomes slack, and the acceleration that Q had of 1.6 meters per second squared is now different because it's no longer attached to this string. So it will move under a different acceleration up like that and reach maximum height at this point, where it's going to have a final velocity 0. At maximum point, it will have a final velocity 0. We don't know how much distance it covers, but at least we can be able to calculate its acceleration that way. Let us call it acceleration 2. So let's see what we have. At this point, we've still got its component down the incline, and the component of its weight down the incline, I think we worked it out here, we got it to be 3.2 newtons. So this will be 3.2 newtons, and it's going that way. There is no force that is pulling it up the incline. So if we were to resolve upwards like that, we're going to use F is equals to ma. The force which is acting on it up the incline is no longer there, so it is 0, minus the force which is opposing that, which is 3.2, and this one will be 0.4 A2. Remember, it's A2 that we want, so A2 is going to be equal to negative 3.2 divided by 0.4. This is like 32 divided by 4, and this will be 8 negative, because there is a negative there, negative 8 meters per second squared. That will be the acceleration that it will be having like that. So let me again find the time taken from the instant that the particles are released until Q reaches its greatest height above the ground. There are two values of T that we are supposed to work out. The first T is to work out the time it moves from when it is released from this point all the way to this point when the string becomes slack. The second value of T will be from this point to when it reaches maximum height. We can start with either one of them. So let's see if we can be able to work out the T here. Now the U that Q had initially before being released was 0. The V it has at this point is 2 meters per second. Notice that I'm talking about the V with respect to this point. This V is with respect to this point, so don't confuse the two V's. V is always taken to be the final velocity for a certain set of values that are given. If u is 0, then the v for that motion is 2 meters per second. But here, the v for this motion now becomes the u. So u will be 2 meters per second, but its v will be 0. So here I'm talking about a situation whereby u is 0, v is 2 meters per second squared. The acceleration, we have it was 1.6 meters per second squared. Now we want the t, and the t can be given by v minus u over a. This is the first value of t to move from this point to this point. So I'm going to call it t1. t1 is going to be equal to, this one will be 2 minus 0 over 1.6. Let me see what that gives us. This gives me 1.25 seconds. That is t1. Let me look at t2. For t2, we have this set of values. V is 0, u is 2 meters per second, the a is minus 8 meters per second squared, and we want t2. Again, we can use the same equation. T is equals to v minus u over a, because all the values are there. But this time, we are going to work out t2. So t2 is going to be equal to v, which is 0, minus the initial velocity, it was 2, divided by a, which is minus 8. And this one will be minus 2 over minus 8, which will be 2 over 8, which will be 1 over 4, which is 0.25, again, seconds. So the total time, because that is what the question is asking, the total time will be equal to t1 plus t2. And this will be 1.25 plus 0.25, and this will be 1.5 seconds. And that is how you would work out the part 2 of question 6. Let's go to question 7. In question 7, we are given that a small ring of mass 0.2 kg is threaded on a fixed vertical rod. The end A of a light inextensible string is attached to the ring. The other end C of the ring is attached to a fixed point of the rod above A. I think all the information is given there. A horizontal force of magnitude 8 newtons is applied to the point B of the string, where AB is 1.5 meters, BC is 2 meters. The system is in equilibrium with the string taut and AB at right angles to BC. So the mention of equilibrium, we remember the conditions for equilibrium that we are supposed to use in mechanics, and that condition is that the resultant force on a particle is 0. Part 1 of that question is asking us to find the tension in part AB, find the tension in part AB of the string, and the tension in part BC of the string. So this part and this part, and for 5 marks. So let's see what we need to write down. First of all, the mass of this ring is 0.2 kg. So definitely one of the forces we have here is the weight of the ring. And this weight will be mg 0.2 times 10 Newton per kilogram we get 2 newtons. So there is no problem with that. And then the angle, of course this one is 90 degrees, so you can work out this angle or even that angle and so forth. I don't know whether this distance is given, but if it is not given, we can easily get it to get the hypotenuse of this triangle. It's just some information that I'm randomly picking from here. The tension in AB, we can call it T1, while the tension here, I can call it T2. The reason why I've drawn the tension that way, T2, to point in that direction, is because I want to find out what amount of force does that string apply to this point. But if I want to find out what amount of force the string applies to point B in this direction, then I've got to come this way, in which case I'm going to call it this one T1. So remember, there is also T1 here. I mean T2. There's T2 here, T2 there, T1, T1. Now, if this ring is like this, then this thread is pressing the ring in this direction, and there we've got the normal component of the contact force at that point. But I think we've been told that the rod is smooth. The rod may be smooth. I don't know, but let me see. I don't think it is mentioned here, but it's mentioned in some other parts here. Find the coefficient of friction between the ring and the rod, So there must be some friction force there. So is there any other? Let me see what this 80 newtons is all about. A horizontal force of 80 newtons. This much is applied at that point. So what are the forces which are acting on the ring? One of them is the normal component of the contact force. The other one is its own weight. I'm not sure whether this ring is about to slide. Yeah, we are told that the equilibrium is limiting with the string on the point of sliding up the rod. But even before we read this, they are assuming that we are able to solve that part 1 with information here without looking at this. So I don't really need the information from this point in order to solve part 1. So let me see whether I'm able to do that from this point. The system is in equilibrium with the string taut. So I will come here. The best point to look at is point B, whereby I look at the forces to the right. I can go ahead and resolve T2 in this direction. I'll have a component of T2 in that direction. I can also resolve T1 in the same direction, a component of T1 in that direction, in which case I might need this angle here and also this angle. So there is all that. So let me look at a much neater diagram to do that. So there is T1 here, and there is that component of T1 in this direction. So you can say this one is T1. If I call this one to be theta, then this one will be T1 cos theta. There is also T2 here, T2 there. So there is a component of T2 in this direction. Don't worry about the relative lengths of T1 and T2. I'm just putting them to have different lengths because I want to just draw them separately. So there is T2 again cos, I can call this angle alpha, cos alpha. So is it possible for me to be able to work out all that information? Can I be able to work out this angle, for example, because that will be the trick, or even this angle here. Let me call this angle beta. Because I have the adjacent and the opposite, I can talk about tan of beta Remember, it's the angles that I want, because I want to resolve T2 in this direction. So if I get beta, and I know that this one is 90 degrees, I can be able to subtract beta from 90 degrees to get alpha, and that will enable me to get this. And by getting alpha, I can get theta because I know the whole of this is 90 degrees. That's why I start from this point, because there is always a reason why you are doing something. Remember where I started from. I'm looking at this point here. It's in equilibrium because I want to ask myself, what are the forces which are acting at this point? It is T1 and T2. Now, they are not in the standard directions that I would want to resolve. So that is why I would want to resolve T1 horizontally to the left, and of course also vertically downwards. Resolve T2 horizontally to the left again and vertically upwards. And then, because this point B is in equilibrium, then I will say T2 cos alpha plus T1 cos theta is equal to 8. From there I can get some kind of equation, because at least I've got one expression from which I can start working with. And then after I resolve vertically upwards, for instance, let me use a different color here to get the component of T2 vertically upwards. I can call this component T2 sine of alpha. Sine of alpha. If I know the angle alpha, then it will be very easy to get that. How about resolving T1 vertically downwards here? I will get T1 sine theta. Sine theta. So I can get two expressions, because there are two unknowns, T1 and T2, T1 and T2, I can get two expressions, one using the vertical components, the other expression using the horizontal components, and then I can solve those two expressions simultaneously. That is the idea. So I have to identify the most appropriate angle to use. And remember, I want to work out part 1 without going to the information for part 2. What does that mean? I do not want to use this information here, the limiting equilibrium with the ring just about to slide in a particular direction, because it won't help me, because still I need T1. That is why I've decided to choose point B to be in equilibrium, and I resolve all the forces the way I've shown you. So let's go back. So tan beta is going to be equal to opposite, which is 1.5 divided by 2, and this 0.75. Beta will be equal to tan inverse of this value, which will give me 36.9 degrees. That is what beta is. That means I can work out this angle here, which I can call, let me call it angle K. So the angle K will be equal to 53.1, because since I know the whole of this is 90, then this plus this is 90. In order to get angle K, I need to subtract this from 90 degrees. If I do that, I can be able to get this angle here, because now I consider this triangle here, and I'll be able to say, since this one is 53.6 and this angle here is 90 degrees, then theta is 90 degrees minus 53.1, which gives me 36.9 degrees. Now let me go to this triangle, other triangle here. I know beta is 36.9. And again, this angle here is 90 degrees. So I know that alpha is actually 53.1 because I just need to subtract beta from 90 degrees to get that. Now that I've got the two angles, theta and alpha, I'm going to say that the sum of the components to the left, which is T2 cos alpha, which is 53.1, plus T1 cos theta, cos 36.9 is equals to 8. And here I can say I've got my first expression. The second expression will be obtained by equating this force to this force, because at this point the component of T2 vertically upwards must be equal to the component of T1 vertically downwards. Remember that point B is not a mass that has been put there, it's just a point. Let's confirm that from the question. Let's see. We are told that the other end C of the string is attached to a fixed point of the rod above the ground. A horizontal force of magnitude 8 newtons is applied to point B. So point B is just a point and it's not a mass that has been put there so that we can consider its weight. And that is why the only forces that are acting vertically upwards on that point, at that point, is T2 sine alpha, T2 sine alpha. Sine alpha will be, let me be very careful here, sine alpha, which is 53.1, is equal to T1 sine theta. Sine theta is 36.9. This is of course the second equation. Now from the second equation I can be able to, let me use substitution method. I can make T2 to be the subject. I can have T1 sine 36.9 over sine 53.1. And I have a value for, of course this is T1, I have a value for T2, so it is this value. I'm going to substitute this value for T2 here. It looks a little bit messy, but I think it's not. So for T2 I'm going to write the whole of this. I'm going to say T1 sine 36.9 over sine 53.1. That represents T2, okay? T2 times, there is of course cos 53.1 plus T1 cos 36.9 is equals to 8. And now from this expression I can be able to calculate T1. So let's go on, and now I'm going to find, I can have the whole of this, that, and this, because we can see that I'm going to factor out T1 so that I can have, let me see what I can get from there. Now the whole of this is going to give me 0.4508 0, 1 recurring. Of course, cos of 36.9 is 0.7997 is equals to 8. Now I can go back to the blue color here. So I can add, here I'm going to get 1.2505 T1 is equals to 8, implying that T1 is equals to 6.397 recurring. We can say it is around 6.4 newtons to 1 decimal place. So that is T1. And now I can come here and get T2. So I'm going to say that T2 is going to be equal to the value of T1, which is 6.4 sine 36.9. Divide all that by sine 53.1. And that gives me T2 to be 4.8 newtons. And that is how we would work out part 1 of this question. Let's go to part 2. Now in part 2, we are told that the equilibrium is limiting with the ring on the point of sliding up the road. Up the road. That tells us that the friction force acting on this ring, is vertically downwards, like that. And because it is limiting, it is equal to mu r. And remember, r is this much. There is this T1 here has got a component in this direction. Let me change the color here so that it doesn't crowd the diagram so much. There is a component of T1 in this direction and also in this particular direction. So if this angle here, we obtained this angle to be, I think according to this diagram here, we obtained this angle to be theta. So since this angle is theta, we are going to observe that this angle will also be theta because this line is parallel to this line. Therefore, this one becomes T1 cos theta. And of course, this one becomes T2 sine theta. So, have we shown all the forces which are acting at this point? I think we have. There is the weight of this ring, and since it is in the vertical direction, there is no need of resolving that. The normal component of the contact force is in the correct direction. There is tension T1, tension in the string AB, which happens to be T1. We labeled to be T1. So I've resolved it horizontally and vertically. And then there is a friction force which is acting vertically downwards. So all we need is now see how we manipulate these figures, in the sense that we are going to say that since this ring is in equilibrium, then the sum of the forces upwards, which will be T2 sine theta. Let me see what we got our T2 to be. Actually, this force here is not T2. I think I've made a mistake there. This force is still supposed to be T1 because it's T1 that we are resolving. There is no direct link between T2 and this point here. So the force which is acting at this point is T1. So this one is T1 sine theta. Let's confirm the value of T1 is 6.4. So I will go here and say, Okay, let me just write these values here. 6.4 newtons. I don't need T2. So I'm going to say that vertically upwards, I'm going to have 6.4 sine theta. Our theta, we had obtained our theta to be 36.9. So this one is sine 36.9. That is T1 sine theta is equal to friction force, which is mu r, plus 2. Of course, we can say this is the first expression. The second expression will be the sum of the forces to the right, which is T1's cos theta, again 6.4, cos theta was again 36.9. This value here, T1 cos theta is equal to R. I need R because of the idea of putting it here. So we can work out R directly. So this one implies that R is equals to, R is 5.1 newtons, just to one decimal place. So I can put that R over there in equation 1, and put it here. So that 6.4 sine 36.9 gives me 3.84, 3.84, and say 2, 6, or 3 there is going to be equal to mu times 5.1 plus 2. We can say that 5.1 mu is equals to, I can subtract 2 from both sides and I get 1.843, and our mu should be equal to 1.843 divided by 5.1, and that gives us 0.3614. You can just say 0.36 will be the value of the mu. So the coefficient of friction between the ring and the rod is 0.36. And that brings us to the final part of this particular paper. If there is any question that you would like to go through, just hover the cursor over the scroll bar and you'll be able to see that particular question. In the next video, I'm going to cover another past paper. If this is your first time on this channel, consider subscribing, because I'm going to be looking at each question paper in details. So consider subscribing to the channel. See you in the next video.